So thank you for your time today. We've got a subject that really could be quite massive that we're trying to fit into about a 20-minute slot. So I'm just going to go through some bits and pieces in relation to that with regards to specifically around being able to understand what can happen. Bear with me. Sorry, my screen has decided. Here we go. With regards to what can happen with regards to EV chargers installations, and there's obviously wide variances on from small devices through to huge ultra rapid chargers. So it's a wide array of things, but I'm just trying to give you some ideas of things to think about when it comes to doing this if you are implementing this kind of technology going forward. So the area I'm going to focus on is actually something called power quality. So the area of power quality relates to everything actually in industry, but today we're focusing on, in this talk, specifically on EV, but it would also relate to other topics like heat source pumps and other things that are going on throughout today in the sessions. So why does power quality matter? There's many factors that affect power quality, and that can range from everything installed within the facility to the EV chargers themselves going into connection into the power network, so to speak. So things like transients, harmonics, reactive power, network unbalance, oscillations and resonances, voltage variations, and flicker, all are factors that we consider. They're kind of like the 7 main key factors that affect what we consider a clean signal into the supply of your equipment or other people's equipment. In this field of power quality, often we're considered experts or wizards. A lot of people think this is kind of crazy stuff, but the reality is we're just engineers trying to have fun and figure out what's going on when we get involved with a lot of these problems today. So, what is power quality? Again, forgive me, I don't know the audience here today. So if some of the stuff goes over your head or you want to talk about any of this stuff offline, I'm more than happy to arrange conversations and Teams calls with anyone to learn more about this kind of thing. But ultimately, what we're looking at is the signal coming into your equipment clean? Does it look like a sine wave, which you can see there on the left-hand side, the ideal sine wave? And quite often it's not. And quite often you don't know that it's not. So you can get things like transients, which are high frequency spikes in the mains. You can get sags and swells, so the voltage can reduce and increase, and harmonics, which is a distortion of the waveform away from a sine wave again. Ultimately, why do we care about this? Well, it doesn't matter what you're producing, whether it's you're producing electricity to charge an EV vehicle, or you're producing products that are making, bottling drinks into bottles. Doesn't matter what that is, be it alcohol, fizzy drinks, or what have you, or food processing. At the end of the day, if the signal coming in to provide you with power to your equipment isn't healthy, your equipment's going to degrade and fail. And likewise, your equipment may not actually operate as it should. In the case of an EV charger, if you've got bad power quality coming into it, it's not going to be able to do its job to charge the EV vehicle properly. And vice versa, if the EV charger is causing problems within the facility, then the transformer is going to have issues, and then all the other EV chargers will be affected and other equipment on the system. What's the impact? Well, globally, it's a massive problem. As you can see there, 230 billion estimated dollars a year in power quality related issues in industry as a whole. And what gets often overlooked is that over 80% of those problems are usually caused within the facilities of the equipment that we're talking about. So they're not coming from the grid and coming through. They're usually less than 20% of issues. And one of the main reasons for that is more and more things are getting complicated in terms of hardware that's being installed, and we'll talk about that in a second. Some of the symptoms. If we don't look after power quality, these are the kind of things that happen: overheating, degrading of components, premature failure of equipment. Maybe the product's longevity is designed to last 7 to 10 years, maybe 10 to 15 years is the design life of the hardware, but it's failing 3 years, 4 years, maybe even in the first year. It depends. And there's a whole host of reasons for that, but a lot of them are related, well, most of them are related to power quality. And one of the big reasons for that really is that the grid is changing, and has been for a very long time, but slowly. And I think I would say in the last 5 years, much more rapidly. So with solar, electric vehicles, EV chargers, wind, energy storage, bidirectional power flow. In addition to that, all of those systems are working together. But on top of that, we've got in factories, upgrading from a motor that may be spinning direct online, so it's connected straight into the grid via a contactor or star delta. It's been upgraded to soft starts and over time then to variable speed drives, which are the same technology that's inside an EV charger at the end of the day. Um, and that I would say in the last 20 years has been a significant increase. So that coupled with what's going on in the factory already, and then the addition to these other things that are going on and higher switching frequencies have an effect on the power system. So what we consider the power quality spectrum, a lot of people refer to it as EMC, and EMC is like the overall name given, but then we kind of break that down into three main areas. So we have harmonics, which is from the fundamental through to around 2 kilohertz or 2.5 kilohertz, depending on where you are in the world and what standard you're adhering to. And then we have super harmonics, which we'll come back to, and EMC is 150 kilohertz and above. So we're talking about conducted emissions, not radiated. Superharmonics sits in the middle, and until recently, people would probably argue it doesn't exist because there's no standard requiring you to measure it, even though there were devices available to measure it and problems being identified with noise being created here. More today, the standards have caught up and are catching up to mitigate the problems that they're seeing here as the technology is shifted, where the technology is creating the noise in the spectrum from harmonics into superharmonics. The standards are now realizing, okay, we're going to have to start putting some measures on this now because we're starting to see issues in productions. Yeah, so we're not talking about EMC today, so that's focused on outside the area we're talking about today. But mainly, why am I focusing on this? Because the technology we're talking about today, the EV chargers, are creating noise between harmonics and superharmonics, depending on the level of technology that's being deployed. And depending on the number of these that are being deployed is a factor. And also, are they being interfered with by the production facility, for example? I have a case where I visited a production facility and their equipment was affecting the charger's ability to remain on comms, which we'll talk about later on. So why should we monitor the power quality? If you monitor the power quality, you know how the system situation is. You know what you're getting into before connecting your own equipment in. So if you're upgrading or putting new EV chargers in, you've got a baseline to understand how healthy is the system that I'm plugging this new equipment into. That's the most important thing I think that's critical. So having a pre-survey done or putting in some online monitoring that's fixed so that you've got a continual recording over time that you can go back and look over time as you've upgraded. Has it affected anything or is anything affecting you? That's ultimately the key thing really, is knowing that your equipment's going to be healthy, that you're investing in. Problems that can occur are overheating, as I mentioned, premature equipment failure. There's loads of things that can happen. If you're not monitoring, which we found on many cases, not just in the EV world, is if you're not monitoring when an event occurs, and I assure you an event will occur at some point, the ability to actually break that down and root cause analysis that. And it might be that you determine, oh, okay, there was nothing we could do. It was a really bad situation. Something happened from the grid or something else happened and we understand what happened. And you don't spend weeks and months arguing and fighting and trying to investigate a problem because you've got the actual facts in front of you of what occurred at that point in time. Equally, the other way, if it's not your fault, you've got the proof to identify that it wasn't your fault. And that immediately negates arguments over warranty and all other kind of things that go on. Or more importantly, for you and whoever to work together and work closer on resolving the issues that you found, which tends to be the most important thing for everyone. The ability to, understand that an event has occurred and what's happened is quite powerful, and to be able to have that recorded in real time and snapshotted for you is critical, really. You can also produce reports, so you can go back and look before and after and say, well, it was fine before we installed our equipment and it's fine afterwards. Everyone's happy. If something changes over time, you can go back again and look and say, right, okay, something's happened. Some more chargers have been installed. Some more site equipment has been installed, maybe, and you've at least got something that you can refer back to and reference from. And even something like this, so it could be some pre-faults occurred. Maybe there's a trend that something's starting to change on site. It could be a cable breaking down. In terms of EV chargers, maybe one of the vehicles that's plugged in's got a bad battery or is not charging right, and then you start to see that that caused the problem in the charger because now the charger's not operating properly. You could trend that with the recording of the information that leads to you understanding that you might have a catastrophic failure, and you could predict that maybe service or investigation needs to happen. So quite powerful stuff, really, rather than being reactive, being proactive. So if we look at the disturbances I mentioned before, we've got transients, harmonics, oscillations, voltage fluctuations, reactive power, flicker compensation. Well, not flicker compensation, sorry, flicker, which is affecting the lights and other equipment. Ultimately, rapid voltage changes and violence. These are all things that affect your equipment and other equipment on site. The more sensitive the equipment is, the bigger the effects these can have on reducing that. So if I take a step back and we just look at harmonics and what they are, ultimately harmonics are caused by the drawing of what we call nonlinear current from nonlinear load. So a linear load, as an example, would be something like a motor that's just directly powered by the power network, turned on by a switch or a contactor. A nonlinear load, something like a VSD, a dimmer switch in your home, an EV charger, which is using an inverter technology as well. The technology inside that, the IGBTs and the diodes, are creating harmonics, and those harmonics overlay over the sine wave. As a result of that, if you had all the harmonics together, you'd end up with a DC waveform, which is kind of like what you're seeing here in the simulation. So the idea is to get rid of the harmonics as best possible. And the way to do that is with mitigating that by design. Because if you don't, things like cables will overheat. Harmonics travel down the outside of the cable. It's something called the skin effect, not down the center. So if the cables aren't derated and sized proportionately for the type of harmonic load that's been connected, which in fairness to most Sparkies and installation companies, they will have no idea that this is something they need to do, then ultimately the cable can overheat over time and catch fire, burn out, all those kind of things. Other things can occur as well. You have things like resonances and other bits and pieces. So again, we can talk about that another day. So we have some standards. So we have standards in place to try to, these are just some examples, to try and prevent equipment that's being installed causing more problems. And the design of this is really to make sure that A, your transformer's okay, the best possible it can be, and that you don't impact, or the factory doesn't impact, the connection upstream into the grid, which ultimately means they don't affect their neighbor as well. The standards don't really protect the facility. There's a lot of bandwidth in there. So these aren't things you're aiming for. You're trying to avoid getting this high, basically. And a lot of things we mentioned before, you know, there's other things that can cause issues with regards to the transformers overheating, which is your supply basically to your EV chargers and everything else that might be on that same network. In addition to that, that gets overlooked is if there is a voltage distortion created by these devices that are taking this nonlinear current, then that transformer will give out a signal to other devices like motors that 8% voltage distortion could reduce their torque output by 15%. So there's a lot of hidden things that go on if we don't keep our power supply clean and healthy, i.e. healthy power quality. And another thing that's not really mentioned much is something called harmonic loss factor. So these harmonics feed back to the transformer and summate there. And in FHL, if we breach that curve, what we can see is that the voltage distortion from the transformer increases and the ability for the transformer to provide you enough power for your loads gets reduced. So an example here is if we had a FHL of 7, you can see on the left-hand side, the transformer would be derated to around 50% of its capability. And here's a live example of that. If we look at this one here, here's a dairy where they have a 2 MVA transformer, and their spare capacity was only 180 kVA for more loads that they were looking to put on because they had an FHL of 3.2 that we measured. We installed a harmonic filter, which reduced the mitigation down to 1.1, which meant they had an additional 600 kVA for their future loads. So again, that's a whole topic in itself. I don't want to bore you with too much of that, but the importance of getting the harmonic reduction down means that your transformer that's supplying you can keep delivering you the loads you require. Another thing to think about is understanding if you've got metering going on, we can produce things like a thermal heat map that you can see here on the bottom right hand corner. A thermal heat map allows us to understand which frequencies are present. And in addition to that, the effects of where maybe you've got some disturbances and you notice there's some problems on site, we can determine, oh, okay, it was between this time of day and we can see these frequencies were operating. Okay, solar inverters were on then. It could be that they were interfering with some other equipment. So very useful if you're measuring. Again, if you've got external things like lightning strikes and other things, to be able to know that that was something and you couldn't prevent it, and why something's happened is critical, really. And the same with the EV chargers. Maybe you can determine that one of your chargers is starting to fail in advance, and then you can get someone out there to go and get it repaired and fixed. Same thing here. This is a prime example where we were able to identify that there was some high frequency noise being caused by the chargers that was interfering with other equipment. So what options are there to measure and for what, really? You have to kind of be quite careful because a lot of people out there are doing power quality studies and measurements, but the devices they're using can only measure to the 50th harmonic. So they can't even see the noise that's potentially causing the problems. It's a bit like they're blindfolded. Here's a good example. So Units are a brand we promote and use for fixed meters, but they only measure to the 127th harmonic today. So they're covering the standard of G55, but they're not covering the superharmonic spectrum, which is where this equipment's noise typically is going and where most disruptions come from. A device like this, the P-Cube 3 that we offer, it's a very compact device, would measure up to 170 kilohertz. So this would cover the full spectrum, give you reporting, analysis, email alerts, trending of problems, all sorts of stuff, really. Again, not trying to give you a sales pitch, just trying to give you an idea of some devices that are on the market. Here we have Shoven Anu, no different to Fluke. They're measuring up to about the 127th as well as portable devices to do measurements with. And then above that, to measure the frequencies we're talking about today, devices like Eberle or Neo would be ideal for that. And why do we need these devices? Well, if we look here on the left-hand side, this would be something like a VSD or EV charger, B6 bridge, and it has harmonic distortion. So you can see the waveform is not a sine wave. It's kind of like a double hump. On the right-hand side, you have what we call low harmonic solutions. So AFE, active front end. You can get those in EV chargers, I believe, and also in variable speed drives. The problem is they are low harmonic. You can see there the THDI reading is 5%, but they're overlaid with a super harmonic. You can see a ripple over the frequency. That you need specialist equipment to measure, but that is what causes a lot of problems in sites. And the main reason that is you need sampling rates of the devices you're measuring to be more than twice the speed of the switching of the device that's making the noise. And from that, we can determine what the noise is, and we can break down where the problem is, and then we can prove by using mitigation what results would be. So active harmonic filters is one way to get rid of the harmonic noise from EV chargers. We need to look at that holistically. Maybe it depends how big the EV chargers are. If it's a big bank of rapid chargers or if it's a small group in the car park, maybe they're not so critical and maybe the whole plant needs looking at rather than just the EV charger section. And the same with super harmonics. So we have a range of things that can resolve those. So I'll give a couple of examples now as we come into closure on some cases where we helped customers resolve issues from design through to problem solving. So this is a bus depot. We worked with the end from beginning. We worked with the end user, the DNO, the OEM charger manufacturer, the consultant, and the installation contractor to make sure everyone was unified and united in the approach. We went through their system design, working through what they were trying to achieve. We simulated the harmonic spectrums that they planned to generate. And these are heavily dynamic loads. So even if you do simulate, they're not going to operate anything like what the perfect world is. So we installed We didn't install, sorry. We supplied a remote dial-up device, the PCube3, the harmonic filters and the super harmonic filters, so the ADF and the sine tamer, and we had that all in the cloud for the client. And on their first project, it was essential because they actually had some significant problems, both in design of the output of the EV chargers, which we fed back feedback on how they were operating, what kind of noises they were creating, so that the manufacturer could actually modify the software to improve the situation. In addition to that, they did have a problem on a specific part of the job, and we identified what that problem was for them and resolved it with them. And here you can see the results of the harmonic mitigation. So on the left-hand side, in the bottom corner, we've got 1,000 amps of load, and we were keeping the THDI under 5% and resulted in the voltage distortion being under 2%, which is everything's happy. If we move on to another example, these are small chargers in the car park for a facility. In that facility, I forget how many chargers there were, but I think it was about 12 or 15 in total in different banks. And two things were happening. One was the chargers were going offline due to a comms loss, and some equipment in the factory was not so happy. And we measured with the PQBox 300 the harmonic spectrum, so we can understand it was actually super harmonics. And we noticed we had about 500,000 small little transients or high frequency noises that you can see there on the counter in the middle. They weren't bad, they weren't high, they weren't aggressive values when we measured them with the measuring device, but they were frequent enough to be a problem because of the noise spectrum. So we installed a little sine tamer in there, and immediately all the devices came online and the comms started working and the devices could upload their information. As I said before, the data here is showing you that it wasn't high values, but it was enough to be a disturbance. So on the left bottom corner, you can see the high frequency in pink was 100 kilohertz and above, was affecting the communication cables between the devices that were going out via a router. So look, that was very fast and very quick, a whole load of information about the importance of measuring when it comes to EV chargers. I think it's probably the most underrated thing people should be doing when it comes to installing EV chargers as a group or as a bank or as for a factory, for a facility, for a car park, etc., is knowing what is the current situation of the power quality that you're connecting into, i.e. is it healthy or happy? Because if it's not and you put your equipment in and it starts failing, you're going to get the blame. In addition to that, if it is healthy and happy, you can monitor and prove that and then put your devices in and then identify that it's no worse than when it was before. Secondly, if there is a problem, you then know and understand what the information is that's needed to now mitigate that problem that you've created potentially. So yeah, I just wanted to get these points across really in terms of the importance of understanding the picture that you're connecting this into, and it's going to get a lot worse as time goes on. So the more you can mitigate your own problems and projects by having some data beforehand, and the online monitoring is probably one of the better ways to go because you're continually monitoring all the time. So you can always go back and look back and say, well, it was fine here, or we're seeing a trend of this problem there, or get an advance warning as well of potential problems that are coming up for maintenance teams, etc. So yeah, that concludes my part of the presentation today, and just want to say thank you for your time.
Perfect. Thank you, John. And obviously, anyone wanting to learn any more, actually, you could just look up the latest issue of Electrical Review, since you have an article in there all about how we can build infrastructure that can weather a power quality storm. But also, while we have you, people can ask questions, and we've actually had two questions.
Do we have some? Sorry,
We do.
I might have missed them. Sorry.
That's right. Jenna Staley says, is harmonic data collection something that should be considered for new build housing or just for larger commercial buildings with an EV fleet or a large amount of motors?
Oh, that's a really good question, actually. I think commercial buildings and factories, yes. Residential is a bit trickier, I would say. I would say definitely if we could measure in a bank or an area, then I think it's important what's feeding off the transformer. Whether you do it as an individual, like if it's for your house or for something like that, it's quite an expensive solution to provide, right? So I don't think it's probably going to fly that way. But if the connection point's going into multiple, if it's a bank in a street or something like that, or a charging station in an estate, I think definitely it should. It's going to come down to the power levels and how big these chargers are. If they're small, I would say no. Probably not needed. But as you get multiples of small and things start going wrong, then definitely an investigation would be worthwhile for that. But if it's commercial buildings, industrial facilities, I would definitely say yes, because they get a lot more complicated with the types of loads they've got, right? So they might have HVAC on the roof, ground source heat pumps, solar, battery storage. It starts to get a lot more complicated, but usually the last thing in gets the blame for everything. So if you've got an understanding of how it is first, I would say yes.
I think it's less important for if your EV charger at home doesn't work, it's annoying, but it's not business critical.
Definitely not. And the costs outweigh probably just getting another one sorted out.
Yeah, exactly. Someone like DPD definitely needs to make sure that their vans are charged. So
exactly,
that's a bit more business critical.
Exactly.
We also had a question from Elena. She said, or he, I actually don't know. They say the distribution transformers do not have low voltage regulation. Do you think that the design of these transformers should be changed to keep the low voltage within the limits?
Oh, that's a tricky one. Almost no comment on that. I think distribution transformers, well, it comes down to two things. One is this, it's quite complicated. Power quality is quite complicated, right? If we specifically talk about harmonics, if you oversize the transformers and your cables, you probably won't have a problem, right? But typically today, we're not designing from scratch unless we're upgrading a transformer from the beginning. So what's happened over time is that those transformers that are in place that may have been there 10, 20, 50 years, depending on how well they've been looked after, the loads have changed to them. So it's not for the transformers typically to have mitigation because they don't know what's being connected to it. So the key thing is, again, putting the monitor in and then putting the mitigation in within that facility. One way to do that is you could put for example, active harmonic filters at the central part of the transformer for the facility, and then have that modular. So if you have that modular, as you expand your different types of loads and put more and more strain on the transformer, you can expand the mitigation for it, kind of like sound cancelling headphones, the same kind of approach to the noise created,
Yeah, that's perfect. Thank you, John.
Okay.
And you bang on time.
Oh, there we go.
So, very efficient. Thank you very much. And obviously, if anyone wants to hear more from John, obviously they could reach out to you, or
sure,
they can go read your latest article.
read my article. Yes, absolutely.
Yeah.
More than happy. And thank you again for your time. Appreciate it.